So today's talk is about optimizing RADOS GateWay object storage on mixed media through storage classes and Lua scripting. So my name is Curt Bruns. I did this work with Anthony Diatri, and we basically did some work that we put into Quincy to show how to basically optimize your object storage. And object storage in this case is RADOS GateWay objects, not RADOS objects. And through the storage classes and Lua scripting that was put into Pacific. Get to the next slide here. So my name is Curt Bruns. I'm a staff software engineer at Solidigm. I also contribute to the SPDK project. And Anthony's my colleague. Are you online, Anthony? Introduce yourself. I know he had some things happening this morning, so I wasn't sure if he was going to be able to join right away. But anyway, Anthony works at Index Exchange. He's a principal engineer there. He's written a book on Ceph, Learning Ceph, second edition. He's also published some papers that are listed here, and he contributes to the Ceph project in the documentation sections. So we're going to start at a high level, talking about what are the characteristics of a typical Ceph RADOS gateway deployment. And any of you that run a RADOS gateway know you get a wide variety of object sizes being stored in the cluster. Workload is very read intensive, mostly 80%. If it's a data center workload, it's probably 80% reads, 20% writes. If it's an AI workload, you're probably even more reads than writes. Probably I've seen numbers up to like 5,000 to 1 reads to writes on a AI intensive workload. Once a model's trained and you're just doing inference. So that's very small writes, like 0.01 drive writes per day type of activity into your backend. But when you're sending these writes, these large objects demand, a high read throughput, and they want a lot of bandwidth, and they don't cache very well. Small object operations are kind of at the other end of our four corners, right? So you want IOPS, you want low latency, you want to be able to get those objects in and out of the cluster quickly. So you kind of have these competing demands, and they conflict, right? So you don't care about latency so much for your large objects, but you do care about that for your small objects. So typically hard drives are the traditional choice. You have great dollar per terabyte. But when you start getting these hard drives that have all these objects on them and their interface is legacy, you're talking SATA, you're talking 100 to 180 IOPS. The bandwidth isn't fantastic on those as well. So then you start getting these bottlenecks in your cluster. It's exacerbated with these ultra dense servers. You can get 90 drives per chassis in some of those super micro ones. These storage admins were all under pressure to minimize capex. And so the dollar per terabyte's great, but then you could suffer in performance. So it's kind of this whole balancing act, right, of IOPS, bandwidth, latency, resiliency, and how much everything costs. SSDs are great, but sometimes they've been prohibitive in cost. I think they're getting much better now, but how to use them efficiently is important. And so if you're balancing these IOPS, you're balancing bandwidth, one way to do it is to do multiple pools, right? So you can kind of put these large objects in this kind of cheap pool of, say, hard drives or high capacity SSDs, and then create another pool, like erasure, well, you would do erasure coded HDD pool for cold data or large objects that aren't touched very often. But then you use for these small objects that require quick access, you could do a replicated SSD pool. Call that hot data, if you will. So yeah, you kind of have this in RBD layer already, right? Where there's this concept of putting these multiple storage pools inside Ceph. RADOS Gateway can support this as well. The way they do that is with the S3 protocol feature called storage classes. You set up a storage class, and then you can do basically steering these storage classes to the different pools. So you create these large, cheap, deep, slow storage classes, hard drives, or bulk capacity SSDs for these huge objects. And then you use your TLC type SSDs, which is a faster SSD for small objects and high IOPS. So what the kind of issue is, or what has to happen, is you need the user then to basically attach a storage class as an HTTP request to tell it what storage class you want to store this object into. So once you start having the end users make these decisions on what storage classes they need to use, you can get compliance problems. Copy and paste scripts, right, of storing an object into a certain storage class could be invalid, could be wrong, and so that could be a problem of basically not getting the storage into the right pool. And so some more background. Around BlueStore, Ceph allocates something called min-alloc size of underlying storage. So for every write into the cluster, Ceph BlueStore is going to allocate min-alloc size of underlying storage. So even if you write 1 byte, the min-alloc size is 4K, so that's what will be allocated. Now SSDs also have kind of this underlying min-alloc size, if you will, but that's called indirection unit. Historically, SSDs have kind of matched the 4K indirection unit, but if you don't match indirection unit with the actual write size, you can get imbalance in your drives, and you'll end up being inefficient use of your drive. So the latest QLC drives are great for hard disk drive replacements. They have faster writes, fast reads, and they have density as high as 1 petabyte per rack unit. So that's in kind of the ruler form factor. You can get a lot of storage in a small amount of space. The downside to the QLC is the fact that the IU, because of the cost, you want to eliminate some of the RAM that's on the SSD. So you create this indirection unit as 64K, which is now 16 times higher than that 4K. So every time you do a write, you're going to allocate 64K on that SSD to create that write, which can end up making this overhead worse. And it can even be where it's really bad around small objects. And then if you use erasure coding on top of that and you're doing small objects, you're going to have issues with basically what we're going to call allocation amplification. So this is classic space amplification, where you basically are allocating more in the SSD than you actually need to use for your data. And so there's an example down there for large objects, you'd want to put them into QLC pools. And small objects, you'd put them into TLC pools. And so QLC is quad level cell, newer technology where you can store 4 bits per cell in a NAND device, and then TLC is 3 bits per cell. And like I mentioned, IU is indirection unit, which is kind of the abstraction of how the SSD allocates its storage. So we talked about a little bit about space amplification. In Ceph, there's 2 areas that I call replication and allocation space amplification. Triple replication, which is the default for pools created in Ceph. That always means you're at least 200% replication space amplification, because you have your data plus 2 copies of it. So you're basically allocating 2 times more, or 2 additional copies for every 1 data copy. Now, a problem you can have, what I mentioned, is writing less than that min-alloc size we just talked about. That causes allocation space amplification. May not be that big of an issue with 4K. You have that kind of high granularity indirection unit. But once you start getting into these larger indirection units, 64K, every time you do a write, you're going to allocate at least 64K. So this example down here shows you, so if we just had a single 4K write, we're going to have our normal replication amplification, right? We're going to make 2 copies of it. So there's our 200%. But if we're writing that into a 64K indirection unit, you basically have your data, but then it's going to have 60K of just kind of allocated space that's not been written to. So you're really losing a lot of space in your drive. This is obviously a contrived example that's worst case, but you're going to get that across your 3 copies as well when you do your writes into the cluster. That's going to allocate 3 different areas to write, and all of them will be 64K each. So a single 4K object allocates 192 total. And if you do just the 64K of data plus 128K of the replicas, that's 47 times more data than you needed to you allocated 47 times more than you actually needed. Again, this is not common because you probably won't be writing just small 4K objects, but it is a potential problem with these larger IU drives. And so just to show this in data out of a Ceph cluster, I set up a pool, triple replication QLC pool, and basically that's just associated with the device class of QLC. Set up the pool, and then did a single 4K write into that pool. And this could be an example of, say, like I had mentioned before, having the user control where these writes go if they mess it up and they send QLC class and the HTTP request header as a storage class. It's going to go into that QLC class, and if it's just a 4K object, you're going to end up getting kind of this extra bytes written allocated into the cluster. And then space amp for allocation is 15 times, but truly the total space amp that includes allocation plus replication is 4,700%. So 47 times. This is exactly what we showed on the last slide, but this is actually using Ceph tools, pool stats, OSD, replication stats, those things to pull that data out of the cluster. I wrote kind of these scripts here to basically pull out space amp from a cluster, and it can work on a whole cluster, but I was just doing this simple kind of one RADOS object stored in the cluster. So what do? We need to simplify storing objects into the correct pools. Don't rely on the user to make the correct choices all the time on where they want the data to go in the pools. We can do things smarter as storage admins. So for those of you that are familiar with it, the Pacific release brought the ability to have Lua scripts basically get hooks into different RADOS gateway events that happen. And if we use these Lua hooks to basically look at the put objects, and so when objects get put into the cluster, we can look at the storage class, and then we can do something with it. We can make decisions on how to handle that. We can override it. We can, if they didn't have a storage class on it, we can add one. The example that I did in Quincy that's in there now is basically look at the size of the object that's being written. If it's over a certain threshold, then we put it into the QLC class. If it's less than that, then we put it into the TLC class. So create two pools and steer the objects accordingly. And so if we had a TLC pool with 4K IUs, we would create that for small objects. And then we would have this QLC pool with 64K IUs that you only want to store, say, objects greater than 64, so you wouldn't be over allocating. So just a little more background on the QLC and TLC devices. So you get QLC SSDs, which are kind of these large, up to 30 terabyte drives. They have NVMe performance, or NVMe SSDs. They have competitive reads with even TLC devices, and a total cost of ownership competitive with hard disk drives. Because they're large bulk devices, they can store up to 30 terabytes. They can do about, just under half a drive write per day, but you won't really get near that typically in your cluster. And we were talking, 0.01 drive writes per day, so their endurance is great. SSDs rarely run out of endurance nowadays. They're so large that it's hard to fill up an SSD every day, a drive write per day. Now TLC SSDs are fast writes and 4K IU I talked about that can minimize your space amplification. And like I just talked about in the last slide, so we're looking at this storage class header when S3 objects get uploaded into the cluster. Then we direct them to the proper Ceph pool in the back end. The example I talked about, we're going to steer it by size. Other things are available. You can look at the RADOS GateWay Lua page on the Ceph site, and you can see all the different headers and different HTTP methods and things that you can actually hook into with Lua. So yeah, there's tons of different ways you could kind of slice this and handle your front end of RADOS Gateway. One thing that we had to do as well is, we talked about this 64K IU in the QLC devices. When you create an OSD, that's when it decides what min-alloc size to use. And so it's nice to know before you create the SSD, before you create the OSD, obviously, what the min-alloc size of that SSD, what's its optimal write size is what it's called. So there's an optimal I/O size available in Linux that's on inside the sysfs. So you can query that, look at what the drive's optimal I/O size is, and then set your min-alloc size accordingly. And then you spin up your OSD, and its min-alloc size will match that. So these are some of the changes that went into Quincy. So I put this in where you automate the min-alloc size OSD composition. 4K has always been the default. Well, not always, but it's been the default for the last couple of releases. We use optimal I/O size, and it's, like I said, it's in sysfs. This is false by default, so your OSD will default to 4K min-alloc size. But if you turn this on, when the OSD is spinning up, it'll actually look and see when it queries the drive that it's going to create an OSD on, that it'll use optimal I/O size. So, for example, in my system, there's two NVMe drives. One of them's a QLC device, one of them's a TLC, and if you just search it, it'll return the optimal I/O size. Sometimes it's 0 if it doesn't support that, and so if it's 0, we'll just do 4K min-alloc size. So this is the RADOS Gateway Lua changes that had to be made to support this case here. So we created, you had to make storage class header writable. It was readable in the past, and so if you make it read-write, then we can actually modify these storage class headers as the objects are getting put. That's how we're doing it. We're just looking at it on put. You could change it on gets, but that wouldn't do much for you. Anyway, the Lua class, or the Lua script here, modifies storage class based on size. It's pretty simple. We look at this RADOS Gateway op being a put, and if it's a put, then we're going to do something with it. We say if the storage class is empty, then we're going to look at the content length. And so if it's greater than 64K and there's no storage class, we'll just change it. We'll make it a QLC class. Obviously, all your pools and your device class and your storage class handlers in the back need to be set up, right, so that these pools are created and that they know how to set these into the proper pool. But that's the that's the zone setup and things like that. And if it's not greater than 64K, then it's going to attach standard to it. Standard's the default storage class, and so that'll just get put into whatever your standard pool is set up for. In my case, it was TLC. And I did, in this example, we only do it if there is no storage class. If a user did attach a storage class, then it's just going to let it fall through and not change it at all. That was just my example of how to do it. Obviously, you could, as an admin, you could change it to however you want. You could force it and just change no matter what the user put in on the storage class. You could change it with different, controls and things like that. But simple example, just showing how to steer things. And so finally, once we've done that, we go back to our example of a user putting a 4K object and a 64K object. This time, they don't have a storage header attached to it. Just showing that the RADOS Gateway Lua script is working, checking the object size and routing it to the proper pool. When we come down here, we see we do have a 4K object stored in our default, which was built on a TLC pool. And we get our 200% space amp. Like I mentioned before, that's just what you get with Ceph with triple replication. You're going to get 200% space amp. And space amp total is 200%. Makes sense on this 4K object because it hit min-alloc size, and so it allocated 4K. copied it twice. Makes sense. A 64K object was stored, and it allocated exactly well, it allocated 192K, which makes sense, and it wrote 64K and 2 copies, and so it also has a space amp of 2, so 200%. And so we simplified the routing of objects to the optimal pool with the RADOS GateWay Lua inside the um, inside the data path as objects get put into the cluster. Here's some references on some papers and presentations. These are the pull requests that put the OSD query for optimal min-alloc size per an SSD, what it says for its optimal I/O size, along with the RADOS GateWay Lua updates and the example script. Here's some RADOS GateWay Lua I was talked about earlier, where you can look at the different HTTP pieces that you can look at with Lua. It says what's read, write, iterable, so those things are listed there, so you can see how to maybe do some fancy things with your RADOS GateWay data path. This is our email here. I don't know why mine went .com twice, but you don't need to put .com twice. This is a great space amplification table that Mark wrote, and then there's also a TCO calculator that's pretty neat, putting in like hard drive or SSD capacities, how many, how big your storage is, and things like that. You can look at what is the total cost of ownership that SNIA has calculated for you. So that's the presentation. That's what we did with Quincy, and an example we put in place on basically modifying and optimizing your storage, especially having mixed media and this QLC devices that have a larger IU, how to basically steer things to the correct pools and make your storage efficient. Any questions, comments, anything? All right, well, that was the rule of 15 seconds. I hope everyone has a great day, good evening, wherever you're at. Appreciate your time. Thank you.